Hello friends, this video on solid states part 14 is brought to you by examfear.com. No more fear from exam. Now we'll talk about the closed pack structures. So if you see a typical lattice or typical crystal, they are closely packed to leave the minimum vacant space because that will make it more strong. Correct? So now we'll understand this. So if you see in the solids, the constituent particles are closely packed and leaving beside the minimum vacant space. There will be almost nil space. So let us consider a constituent particle as identical hard spheres, and they are built in 3 dimensions. If you see, there are 3 dimensions, right? So let's start building this. This is something which we see NaCl. Let's build this. To build this, let's start with 1 dimension and then we'll do a second dimension. First put this in the 1 dimension row and then we'll try to put 2 dimension, 1 XY, and then we'll put in 3 dimension. Right? In 2 dimension we have 2 options, square packing and hexagonal packing, and 3 dimension again we'll have square packing and hexagonal packing. So we'll study this now. We'll first pack in 1 dimension. We have this now item because we are assuming that this closed pack structure is made of spherical hard spheres, right? Spherical objects, or they are hard spheres. They are identical hard spheres. So let's take identical hard spheres and let's try to build closed pack structure. So first we'll create the 1 dimensional, then 2 dimensional, then 3 dimensional. Correct? So let's try the 1 dimensional thing. See, 1 dimensional, there is only one way to arrange the identical spheres, and that is to arrange in a row, touching each other. Correct? That's it. This is the only way. So each sphere will be in contact with 2 other spheres, because we talk about this sphere, it is in contact with 2 spheres. Because here also, don't think this is the end. There will be a lot of spheres on the left, a lot of spheres on the right. This is just one segment you are seeing. So here also you'll have 1 sphere here, 1 sphere here. So you take any sphere, each sphere will be in contact with 2 neighbors. Right? So here I'll introduce a new term called coordination number. See, coordination number, or I'll use this number. Yeah, coordination number is nothing but the number of nearest neighbor of a particle. Let me write it. Number of nearest neighbor. Nearest neighbor. So this number of nearest neighbors will tell you the coordination. For example, in this case, you take 1 particle, there are 2 neighbors. Coordination number is 2. If you take this guy also, there are 2 nearest neighbors. So coordination number is 2 for 1 dimension. So in 1 dimension case, the coordination number is always 2. Let's talk about 2 dimensional packing now. So you have this 1 dimensional packing already done. So you can either arrange in this fashion. Correct? So in this case, if you see a square here. Correct? So in this case, what I'm doing, the second row is placed in contact with the first row. And they are exactly above. If you see in this case here also, you'll see the same pattern. Correct? So all the spheres are aligned both horizontally and vertically. You see, horizontally and vertically, all the spheres are aligned. This is called A type pattern, because if this is my A, this is also A. Why it is A? Because if I am assuming this is one style, the next layer which I joined is also same style. Right? The same style. This is called AA type pattern. Right? A type pattern. So in this case, if you see each sphere, here there will be a lot of spheres added. So don't take the end ones. Here also there will be a lot of spheres added. Here also a lot of spheres added. It will be like that. Right? So let's take this guy now. So this sphere is in coordinate how many spheres? 1, 2, 3, 4. So this sphere is in touch with 4 other spheres. So the coordination number is how much? 4. Obviously, because each sphere is in touch with 4 spheres. Talk about this sphere. It is in touch with 1, 2, 3, 4 spheres. So the coordination number is 4. Now Now, if the center of the four immediate neighbors, whatever four immediate neighbors you have got, right, in this case, you join these center of this, you will get a square. And that's why it's also called square closed packing. Please note, this is also called square closed pack. So that was one way. Let's try another way. So you have one dimensional packing I have done. The next is, instead of putting just down, let's try to put the circle in these gaps, right? So the spares fits into the depression of the first row in this pattern. So if you see, if this was my arrangement A, is this the same arrangement? No, it is little different, right? It is little pushed, right? Because there is a gap here. So this is the arrangement B, and the next will be this arrangement. So if you see this arrangement exactly same. So this will be again be arrangement A. Again this arrangement. If you see this and this are exactly same. So B. So this is nothing but AB arrangement. Here the second row is placed above in a staggered manner, such a way that the spheres fit in the depression of the first row. So with this, it has less free space. Less free space. It is more compact, right? You can make out this, the less number of voids. If you see, the space is more here, empty space. Here empty space is less, right? More compact packing and better packing actually. Right? Now if you talk about any sphere, you take this sphere, and please note there are other spheres here, so don't take the terminal spheres for coordination number, take somewhere in the middle. So if you take this sphere, this is in contact with 1, 2, 3, 4, 5, 6. So each sphere is in contact with 6 sphere. So coordination number is how much? So coordination number will be 6. Why? Because each sphere is in contact with 6 sphere. So now if you join the center of these spheres, for example, if you take this sphere, there are 6 spheres. If you join the center of these spheres, what you get is hexagon. Correct? And that's why it's called 2D hexagonal closed packing. This is 2D square closed packing. So in case of square, there are two possible options, and I've discussed this. In one case, square closed packing, not that efficient. You just place one layer just above the other, and this is called AA packing because all these are symmetrical. This is called AB packing. Why? Because this is layer A, this is layer B. Again A, again B. Coordination number is 6. Why hexagonal closed packing? Because if you join the center of all the 6, if you take any atom and all the neighboring 6 atoms which touches it, if you join the center of those, you get a hexagonal figure. So it is called 2D hexagonal closed packing. Why 2D? Because we are talking only about 2-dimensional now. Now let's do a 3-dimensional packing. So now we have seen that till now we have two kind of 2D pack. So we have to try 3D pack for the same, right? For both the options. So let's first try the 3D pack for square packing, and then we'll try 3D packing for hexagonal packing also. See, for square packing, it's pretty simple. This is how it looks. This is one layer you form, right? You just keep putting one layer over another, and you get this, right? You put this second layer over the first layer such a way that the spheres of the upper layer are exactly above the first layer. So if this is my first layer, let's suppose. So my one layer will be 2D layer. This is one 2D layer. On top of that, I am putting a second layer. Exactly same. Then third layer. Exactly same. Then fourth layer. Exactly same. So if you see, if this was my one layer, this is called A. The second layer is also A. Third layer is also A. Fourth layer is also A. Correct? So this type of packing is called A packing. So here the second layer is placed over first layer such a way that spheres of upper layer, for example in this case, second layer exactly above the first layer. And spheres of both the layers are perfectly aligned horizontally and vertically. If you see this direction, this direction, this direction, they are all perfectly aligned. Right? And they are generally found in simple cube lattice. like this. This is a simple cube lattice. They are found in simple cube lattice, primitive cubic unit. Correct? Now let's understand the three-dimensional packing of the hexagonal packing. Square we had done. For hexagonal, this was the arrangement we have seen. This was one layer we had developed. Now I'm going to make it 3D. Now if you see this from this view, this is the top view actually. This is the top view. But if you see it from this perspective, it's almost same thing actually. There are gaps here, right? There are gaps. This is not even. It's not a flat surface. Right? There are depressions. There are depressions here. Correct? So the next layer which I am going to put on this, just to make it more stable, it is better that I put in the depressions. Correct? So in this case, the second layer which I am going to put will be over this first layer, such a way that the spares of the second layer, the pink one, are placed in the depressions of the first layer, that is the green one. This is my layer A, the first layer, and this is my layer B, the second layer. Correct? So now if you see, there are depressions here. Correct? So there only we are putting. Now let's do one thing. Let's take 5 of these atoms, and let me take these 5 atoms in this. Let's take 1, 2, 3, 4, 5. 5 of these atoms. And if you see, these 5 atoms are having so many voids here. 1 void, 2 void. I mean, just touching the void which is making, right? 1, 2, 3, like that. Correct. Now if you see, the moment I have put the other layer, you see that some of the black voids are filled with the red layer. For example, this case, these voids are filled, right? And these voids are not filled, the one in the white and black. Correct? So there are 2 different types of void now. Correct? If you see, some voids are filled with the red layer, some voids are not filled with the red layer. Even after putting the second layer, some voids are still not filled and they are still shown here in the white. Correct? That means there are 2 types of void. So we have something called tetrahedral void and we have something called octahedral void. So the general calculation is, if the number of atoms you are picking 5 in the closed packed structure, the octahedral void will be equal to n and this will be equal to 2n. Also experimentally that is seen, so you can just remember this, that closed packed structure, right, the number of sphere is n, the number of octahedral void will be n and tetrahedral will be 2n. Correct. Now let's understand these voids now, tetrahedral void and octahedral void, in a detailed way. So let's see this tetrahedral void first. So if you see this tetrahedral void first, the way it worked is, if you go back, so if you just observe this part here, right, there were 3 greens, on that one red circle came, right, 3 greens, on that one red circle came. Correct? That's what happened. Now the same thing I am doing it, 3 greens, on that I am putting 1 red circle, just to simplify things now. Right? Now if you try to view it from this angle, this is the top view, this is the front view, this is how it looks. Correct? 3 spheres and 1 top sphere. You see, geometrically this is how it looks. This looks like a tetrahedron, and that's why it's called tetrahedral void. Hope you understand, right? 3 spheres on the corners and 1 on the top. This is called tetrahedral void. Now let's talk about the octahedral void. Now if it is the octahedral void, look at these things, look at this area. Look at maybe 3 green spheres here. On this, we will put the red ones like that, 3. Correct? 3 green in this triangle and then 3 red in this triangle, and that will form octahedral void. Please note, at least 6 atoms are involved here. 3 green here, and on the top We need 3 green here. Correct? So let's draw this. So for simplicity, we have this 3 green. On top, we have 3 red. Now, if you see, this octahedral void is 3 red. Let's see a different view of this. I have a 3 green, and on the top, I am putting a 3 red. This is my octahedral void. Now, if you see this octahedral void from this angle, actually, from this angle, these are 3 greens and these are 3 reds on the top. You get figure like this. And that's why it's called octahedral. Please note, the figure is something in this fashion. You have to see this line, right, which I am drawing is this line. Then only you can be the octahedral void, actually, like that. Correct? So view from this and this is this side. So this is octahedral void. If you see here, 4 spheres touching each other. These will touch, actually, these will touch each other, and there will be 2 spheres here. That's how the octahedral void looks like. There are 4 spheres touching each other, and there will be 1 sphere here on the top, 1 sphere on the bottom. Total 6 spheres are involved in the octahedral void. In tetrahedral void, total 4 spheres involved. Please understand this concept really clearly, because this will help us to solve numericals. For octahedral voids, this is how it looks. Total 6 spheres are involved, right? 4 on this, 2 here, and the tetrahedral void, 4 spheres are involved. Now, having understood the concept of voids, tetrahedral void and octahedral void, so let's understand the layer. So we have put the first layer and the second layer. This is what we have done, right? Now, when we want to put the third layer, this is my first layer, green, second layer is pink. Now, I want to put the third layer, there are confusion. There are 2 possibilities. One possibility is I can cover the octahedral void, or I can cover the tetrahedral void, right? The green ones are my tetrahedral void, and this is my octahedral void. There are so many tetrahedral voids in the green. These are my octahedral voids. So I have so many 2 possibilities. Correct? So if you want to fill the tetrahedral void, then it's pretty easy. I can just use the A layer. The moment I put the A layer, I'll get AB packing in the tetrahedral void will be filled. Correct? So in this case, if I put this again A layer, all the tetrahedral void is filled. You see, it's exactly same. And again I can put the B layer. This is AB kind of packing, where the third layer fills tetrahedral void. Correct? If third layer is filling tetrahedral void, it is AB packing. It is called hexagonal closed pack, HCP. For example, magnesium and zinc, they show this packing. The coordination number is 12. Coordination number is 12 in 3 dimensions, because one atom is linked to 12. You can't visualize actually here 1, 2, 3, 4, 5, 6 and 7 in the bottom, right? There are 12, one atom is linked to 12 atoms, and in this case 74% of the space is filled. We'll do some mathematics on that to find out these numbers. This is hexagonal closed packing. Let me write this. Hexagonal closed pack. Right? That was when the third layer fills the tetrahedral hole. There is another possibility that this is my layer A, this is my layer B. Now I want the third layer to fill this octahedral void. All the octahedral void should go off. Then the third layer has to be in a different way. It cannot be in A or B form. It will be a different pattern altogether, because you want to fill octahedral void. Correct? Then it will be ABC packing. Now we can have the same thing repetition. This is called ABC packing. Correct? Because the third layer is now, third layer fills octahedral void here instead of tetrahedral void. Correct? So in this case, the third layer arrangement is different from first or second. So there is a different arrangement called C. So it's called ABC packing. So this is exhibited by copper and silver. Right? This is called cubic closed pack, or it's also called face center cubic structure. Face center cubic structure. This is what it is called. Here also the coordination number is 12. Coordination number is 12, and here also almost 74% of the space is filled. Same as hexagonal closed packing. This is same. But the name is different: cubic closed pack or face centered closed pack. We'll derive this values later. This is how it looks. If you see, this is my layer A, layer B, and layer C. Again layer A, and this is how you get this picture. If you merge this, you get this picture. Correct? This is my closed pack. Correct? Cubic closed pack structure. And in this case, I had my hexagonal closed pack structure. Something like this. It will go somewhere like this in some dimension. It will be three-dimensional in that form. This was a hexagonal closed pack. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.